So our last lesson of these quadratics is quadratic inequalities. Um, you've solved inequalities both in here and in Algebra 1. Usually that's the linear inequalities. You've even done absolute value inequalities where the solutions are a range of values, right? With an inequality, we have that less than, greater than symbol, and so we describe a range of values or a set of values as opposed to just one answer when it's an equation. Now, everything that you solve can be attached to a graph, and we did have some of these conversations first semester, so that's why the graph is over here. This is going to help us answer the solutions to some of these inequalities below here. Okay, so here's what I want us to just start out considering. When is the graph greater than 0? Now, when I'm talking about 0, I am referring to the x-axis. Okay, we're basically saying that y is equal to 0, which is the equation for the x-axis. So another way to read this question is, when is the graph greater or above the x-axis? Well, it's above the x-axis on the interval, okay, of these particular values, okay, based on where I'm shading that particular graph. Everyone agree with that? Okay, we can physically see that it's above the x-axis there. So let's just use our words here. It's greater than 0 from negative infinity to 2. Okay, so it's this entire interval, and I'm describing the x values here. Okay, it's the set of x values, kind of like when we were describing the increasing, decreasing. Okay. Then it's also greater than 0 on this other side of the quadratic or the parabola here. So from negative infinity to 2 and from 4 to infinity. Okay, then the opposite, when is the graph less than 0? Or again, another way to think about this question is, when is the graph below the x-axis? It's in between 2 and 4. Okay, and then when is the graph equal to 0, or when is the graph equal to the x-axis or on the x-axis? That's at x equals 2 and x equals 4. Okay, so the key feature that we use to answer all of these questions is we need to know the x-intercepts. Okay, the x-intercepts are the points that we switch from being on the x-axis and then being above it and or below it. Okay, so all of this conversation directly leads to an inequality, okay, or even an equation. Okay, so we'll make all these connections about what it means to solve an equation and what this means for the inequalities as well. So the equation of the graph that we were just looking at is x squared minus 6x plus 8. So if we are just simply solving x squared minus 6x plus 8, we're identifying the x-intercepts, which we found to be x equals 2 and x equals 4. Okay, again, I'm just using the graph there. Okay, anytime you're solving an equation, there's always a graph to represent it. And when one side is 0, this again is representing the x-axis. So when I solve this equation, we're basically asking or thinking about, when is this quadratic equation equal to the x-axis or on the x-axis? Now this same thinking applies when we get to the inequality part. Okay, so this reads the quadratic being greater than or equal to 0. Well, the 0 we're interpreting as the x-axis. The greater than, well, if we're thinking of greater than, we're thinking above the x-axis. Okay, so the greater than is referring to above the x-axis. So when you solve an inequality that it is greater than or equal to 0, you are stating the values or the x values that we get the graph to be above the x-axis. Well, we identified that here at the beginning. Okay, we are above the x-axis from negative infinity to 2, and then from 2 to infinity. The solutions, when we write these up more formally, we're going to use the interval notation. Okay, so the quadratic is greater or above the x-axis on the interval from negative infinity to 2. And remember, we use that union symbol when we have multiple intervals combined. So then the other piece of this interval is from 4 to infinity. Now notice that I use these squared brackets here. Okay, these squared brackets are referring to the equal to part, right? When I have an interval, the squared bracket on the 2 means we're definitely including 2. Well, that 2 we're including because of the or equal to. So this is actually saying where we above the x-axis and on the x-axis, right? The equal to part is the on the x-axis. Okay, so then the next inequality, if I just flip that sign, it's where is the quadratic less than or equal to 0, which has us identifying the values that are below the x-axis and on the x-axis. Well, that's from 2 to 4. Okay, and then these last two, I just took away the or equal to part, and notice how this changes the interval. So now we're stating the values for the quadratic that are greater than 0. So the values of the quadratic that are above the x-axis but not equal to the x-axis. So this is negative infinity to 2, but we're not including 2. Remember, when I use that curved bracket there, that's telling us that we're getting to 1.9999999999999. Okay, I can list 9s all day long, but we never actually get to 2. We get infinitely close to it. That's the difference between this curved bracket and the squared bracket. Squared bracket means we for sure include that number. Curved bracket means we get as close to that number as we possibly can. Okay, and then the union with 4 to infinity. Okay, and then the less than, but less than and not equal to are just all numbers between 2 and 4, but not including 2 and 4. All right, so I start this lesson this way just to remind us that when we're solving quadratic inequalities, we're kind of thinking about the graph. We have to solve for the x-intercepts. Okay, so like I started class with, thinking about what we actually need to do before we solve here. We need the x-intercepts, but then we need to find a way of knowing whether or not the graph is above or below the x-axis without actually graphing that. That's something we'll add as we get to the actual problem sets. So go ahead and flip this over. And these are what your last set of problems are going to look like for this unit. Okay, where you get some quadratic, and then it's less than or greater than, less than or equal to, greater than or equal to something else. Okay, when it's equal, or when we have one side to be 0, that's great. When we have one side that's not 0, that'll be the first thing we start with. Okay, come on, focus. Maybe I need some writing now. Why doesn't the camera want to do focus? There it goes. I just needed some writing to pick up on it. All right, here we go. Okay, so here's our thought process. We see the inequality. We need the x-intercepts. Okay, so because we need the x-intercepts, we need to think about how do we find those when we're solving. Well, we do that by either factoring, quad formula, or completing the square. So since we need the x-intercepts, I'm just going to forget that this is an inequality to start, and all I'm going to do is make it an equal sign. And so the first step is just solve the quadratic, okay, just like you would any other solving part. So I'm going to look to see if I can factor, looking for two numbers that add to negative 17 and multiply to 70. Those numbers are negative 10 and negative 7. Since a is 1, I can use the factoring shortcut in that these numbers are part of the factors. Okay, so this factors to x minus 10, times x minus 7, and it equals 0. For a lot of you on the review assignment you got, like day 1 of this semester, when you had to solve the quadratics, a lot of you stopped here. Solving means to give me a value for what x needs to equal. So the thing we need to do next is take each of these factors and set them equal to 0, and then we solve, getting x equals 10 and x equals 7. Okay, so step number 1, solve the quadratic just like you normally would. So either factor or quad formula. The inequality portion we're going to deal with in a kind of a roundabout way. So we're going to draw a number line here, and we're going to place these x-intercepts on that number line. Okay, so we're going to, when we draw a number line, make sure you're giving some context to just, like the number line doesn't need to be perfect, but having some place where 0 is, and then having a scale, and then making sure we can get 7 and 10 on there. So I'm just going to put tick marks representing 1. So 1, 2, 3, 4, 5, 6, and 7. Then 8, 9, and 10. So on the number line, we're going to put circles there. Those circles I'm going to refer to as the anchor points. Okay, they're anchor points that go onto the number line representing the x-intercepts. Okay, the next thing we're going to decide is, do these anchor points get filled in? So do we include these values or do we leave them open? Okay, I'm seeing some of you shake your heads. Why am I leaving it open here? We don't have the or equal to part. Okay, so we are not going to include 7 and 10 on our number line, and then also when we write the interval. So the next thing we need to do is figure out, okay, is it going to be the numbers in between the x-intercepts that make this true, or is it going to be the values outside of the x-intercepts that make it true? It's going to be one or the other. So this will always turn into either an and inequality, okay, where we connect these, or an or inequality where we shade away. Well, to figure that out, we're going to test a number. And to keep this consistent, I'm going to always test a number in between my x-intercepts. So I'm going to test, let's say, x equals 8. What that is having us do is plug in 8 to the exact inequality from where we started. So we're going to check to see, is 8 squared minus 17 times 8 plus 70, is that less than 0? Well, 8 squared, I'm just going to type this all into the calculator. 8 squared minus 17 times 8 plus 70 gets me to negative 2. So negative 2 is less than 0. Is that true or false? Negative 2 being less than 0, that's true. And so what this tells us is the numbers in between these two x-intercepts make this inequality true. And thus, we are describing the values that are below the x-axis, which in this case are the numbers in between 7 and 10. So now, the last piece is just writing what the number line is showing us. It's showing us the interval from 7 to 10. And these are our solutions. So if we were to plug in any number between 7 and 10, whether it be a whole number, a decimal, a fraction, if it is between 7 and 10, it's going to make the left side less than 0. Yeah. We'll get to that. But if it's not true, you do the opposite and shade away. Okay, so the two options that can happen is you can also just shade away. The last thing that could happen here is just no solution. Okay, if we don't have any, or no solution, or all solutions, I guess, are possible. Okay, I don't know that I have any of those showing up on this today, though, so we'll see. All right, well, let's do number 2, and then I'll save number 3 for you all to do, and then I did throw an application on here that we'll do together as well. And again, I'll start the whole process over, okay, starting from the very beginning. So, I see the inequality. I know that I need to focus on the x-intercepts. That's what helps me actually do the solving piece. So I'm going to change this to an equal sign because the inequality part we deal with from the number line and the testing. Okay, so I'm going to add 7, making this plus 20. And we need to figure out where does it exactly equal 0. That's us finding these x-intercepts. If it factors, that would be ideal. And I think this does, because we're finding two numbers that add to 9 and multiply to 20. Those numbers are 5 and 4. And so this factors to be x plus 5 times x plus 4. And it's still equal to 0. Then I'm going to take each of these factors, set them equal to 0, and solve them separately. Getting x equals negative 5 and x equals negative 4. These numbers are the x-intercepts. Again, I refer to them as the anchor points for when I put them on my number line. So this time I'm going to put 0 off to the right. And then list some negatives off to the left, so I at least have negative 4 and negative 5 on here. So negative 1, 2, 3, 4, negative 5, and so forth. On the number line, we're going to put the circles or the anchor points at negative 5 and negative 4. Are these anchor points filled in or leave them open? They're filled in. And they're filled in because of the equal to. So the greater than or equal to means that we are including the x-intercepts for when we describe this quadratic graph being greater than or equal to negative 7. So now the testing part. There is not a whole number in between negative 5 and negative 4. Okay, but we can test a decimal like negative 4.5, especially since we're letting the calculator do that. It won't be too bad. We could also test a number on the outsides, like you could test 0, and you can still get to the same conclusion. Okay, so it doesn't really matter what we end up testing. Again, I'm going to keep it consistent, test a number in the middle. And in this case, that's going to be negative 4.5. So I'm going to plug negative 4.5 back to the original inequality. So right back to where I started. So negative 4.5 squared plus 9 times negative 4.5 plus 13. And we're checking to see is that greater than or equal to negative 7. All right, and I'm going to plug this all into my calculator. So negative 4.5 squared plus 9 times negative 4.5 plus 13, I get negative 7.25. Is that greater than or equal to negative 7? These negatives always make it a little bit weird. This is false. Negative 7.25 is more negative than negative 7, making it less than. So this is false. Okay, so when it's false, the numbers in between negative 5 and negative 4 do not work. And because of how these graphs play out, it means all the other numbers that go away from the anchor points or away from the x-intercepts will work. And just for the sake of kind of seeing how this testing works out, let's just test 0. Okay, because what we're saying is every number from negative 4 to infinity makes this inequality true. Or every number from negative infinity to negative 5 make this true. Well, let's just see. Okay, let's also test x equals 0. So 0 squared plus 9 times 0 plus 13 is greater than or equal to negative 7. I'm expecting this to be true because it's a number that I'm highlighting. Okay, so 0 squared, 0, 9 times 0 is 0. This is 13 greater than or equal to negative 7. Boom, that's true. That is what this is shading towards. All right. Only thing that I have not done is write the intervals here. The interval is negative infinity to negative 5. And then the union from negative 4 to infinity. And I am using the squared brackets there because of the or equal to part. Yeah, go ahead. Question. That the x-intercepts are at 1/2 and 2, which are the anchor points. Then they're closed circles because of the or equal to. I tested 1 this time, and when I plugged in 1, I get 2 is less than 3, which is true. And thus, every number in between 1.5 and 2 makes this inequality true. So our solutions are all the values from 1.5 to 2. Okay, and it's the x values from 1.5 to 2. Okay, one thing that's really nice about this lesson, we have solved so much up to this point now because almost everything we've done after factoring has involved some kind of solving. Okay, and I can just kind of see the reactions here that it's like, hey, we're starting to get this a little bit. Okay, which is cool to see. Okay, now we still need practice with it, and you'll get some practice with the review here. All right, I want to do this word problem just to, it is set up a little bit different than anything we typically see in here. And then maybe I have you do the solving as well, or we can do that too. All right, so a diver jumps upwards with a velocity of 6 meters per second. This V and then the subscript 0, okay, you're good, referred to as, you can hear this saying or read as V naught, or the initial velocity. Okay, so if you ever see a subscript of 0, that's like the starting value of whatever that variable is. Okay, so this is saying the starting velocity is 6 meters per second from the 10-meter board, which is h0, or h0, which is the starting height. Okay, so if you ever see that subscript of 0, think about it as just being the starting value for that particular variable. We need to decide for what times is the height of the diver greater than 10.5 meters. And it says to use the height formula, h equals negative 16t squared plus v naught times t plus h naught, and round your answer to the nearest hundredth of a second. Okay, so here's what I'm looking for with this type of problem. One, because we're trying to describe an interval of time, we should be writing an inequality. We should be writing an inequality and not an equation, okay, because we're describing an interval. But if you look, our equation is not complete, okay, but I am given what each of these values are. Okay, so after I substitute these values in, the height formula is negative 16t squared. The initial velocity, or v naught, is 6, so that's plus 6t. And then the starting height, okay, or h naught, is 10, so plus 10. We are trying to figure out when is the diver's path modeled by this equation greater than 10.5, so above 10.5. So h is 10.5, that's the height. We want the diver's path, so the greater than pointing towards his path, to be negative 16t squared plus 6t plus 10. So again, this inequality, when we think about it in terms of the problem here, is saying the diver's path, when is it greater than or equal to 10.5? Well, yeah, go ahead. Yeah, probably, huh? Yeah, good call. Okay, we're going to change that to just greater than and not the or equal to. Okay, if it said greater than and equal to 10.5, then I should have had that equal to part, but yeah, good catch there. Okay, well, if we're solving this, and we may not go all the way through here just because it's going to take a little bit of time, idea is the exact same. Get one side to be 0, change it to an equal sign. Negative 16t squared plus 6t. I subtract 10.5 and get negative 0.5. Will this factor? No way. Okay, so since this doesn't factor, you need to use the quad formula to find the x-intercepts. Okay, which can get messy. You know what? Why don't we? Let's do it. Let's do it. I'm gonna pause and have you all do the quad formula and take it from here. Solve for t, then the number line. The number line will help you answer the question. Okay? Give you a couple minutes to do so. The quad formula here works out real nicely because we end up having to take the square root of 4, which is great. Makes it a little bit nicer. Okay, so the two values of t that make this equal to 0 are 0.125 and 0.25. Now, really what those t values represents is when the diver is at exactly 10.5 meters. Okay, so the diver reaches 10.5 meters at the first 0.125 and then again at 0.25. Okay, so he's above 10.5 meters from 0.125 seconds to 0.25 seconds. So the total time that the diver is above 10.5 meters is 0.125 seconds. Okay, you don't need to do the interval. You don't need to do the number line. And the reason that we don't need to do that is I'm just thinking about, okay, what it looks like for a diver's path, right? They're going to go up, reach the maximum, and then turn around. So the 10.5 is happening at two places, okay, when he first reaches it going up and then getting it again as he comes right back down. Okay, so 0.25 to 0.125.